Hello, and welcome to our talk, Modular Battery Charging Systems for Industrial Vehicles. I'm Chris Botting. I manage research at DeltaQ Technologies here in Vancouver, Canada. I have 20 years of experience with EV batteries and powertrains. Today, we'll be looking at the requirements for an industrial onboard charger more generally. And then we're going to dive into modular charging systems, what they are, how they work, and what the benefits are. Then we'll finish up with a quick overview of DeltaQ and key takeaways. Non-road mobile machinery, which includes excavators, tractors, mowers, and forklifts, are a major source of CO2 and air pollution. The solution is to replace dirty diesel and two-stroke gas engines with zero-emission battery electric powertrains. This is driving a growing demand for industrial batteries and for onboard battery chargers. So, what are the requirements of an industrial onboard battery charger? The first requirement is simply to survive in a harsh industrial environment. Ruggedness and reliability are mission critical. This means that the charger manufacturer should use a rigorous design and validation process. DeltaQ uses techniques borrowed from the automotive world and modified for the unique needs of off-road markets. We designed for several environmental stress factors, including mechanical, electrical, thermal, humidity, and corrosion. These stress factors are also combined in highly accelerated life testing. On the mechanical side, this includes extreme one-time and repetitive shock and drop events with forces up to 100 G, much higher than is seen in on-road vehicles. Vibration testing on a shaker table simulates a lifetime of harsh use. During the design and the validation process, we iteratively make use of halt testing, that is, highly accelerated life testing. This is an extreme test-to-failure regime, and it's a valuable tool because it lets us rapidly find weaknesses in a design. Halt testing combines several different stress factors, very high levels of vibration, and very high levels of thermal shock, which combine to create failure modes in power electronics. Sealing is a critical aspect of charger design, particularly in an outdoor or a wet environment. But even in an indoor application, there's often condensation, cleaning fluids, washing or spray down of the machines. And sealing is needed not just for the charger enclosure, but for other details like external cooling fans, displays, buttons, the interfacing connectors when they're mated. You're generally looking for an IP rating of at least IP65 or IP66 for spray and pressure wash. And in some applications, you may also need to survive submersion or steam cleaning. At DeltaQ, we've drawn on automotive standards to lay the statistical groundwork for our validation test plans. So by careful selection of the test severity, duration, and sample size, we can actually quantify our product reliability. The key is to understand your users and then to design and test so that you can withstand a severe user. You can see this here graphically. The orange curve represents the distribution of users and how often they stress the product. The average user on the left is in the middle of the distribution, but the severe user on the right is in the extreme tail of the distribution. This severe user is going to subject the product to more extreme and frequent abuse. Now, the gray curve on the right represents the strength of the product itself and its variability. Where the gray curve overlaps with the orange curve is where the product failures occur, due to a combination of high user stress, orange, and low product strength, gray. The failures seen by the severe user are in the yellow shaded area of overlap. The average user should actually see no failures because there is no overlap with the distribution of product strength. So for example, if we design our test plan to give us 97% reliability at 50% confidence level, with a 1 in 500 severe user, that is a 99.8 percentile user, we should see at least 99.5% reliability in our total field population. The power required of an onboard charger will depend on the size of the battery and how fast it needs to recharge. The battery, in turn, will be sized to meet the energy and the power demands of the vehicle. If this is an application where a diesel or a gas engine is being replaced, then the more powerful the engine is, it'll require a larger battery and a more powerful charger. For compact mobile machinery, the onboard charger is usually between 1 kilowatt to 10 kilowatts. With larger vehicles or high duty cycle, high power applications, they may demand higher charger power, but this can often be met with off-board DC fast chargers instead. The battery voltage levels will usually be around 48 volt to 96 volt nominal, with maximum charge voltages of 60 volts to 120 volts. This corresponds to common global limits for safe working voltage. Larger vehicles with higher traction power levels may require higher voltages, like 350 volts nominal, 400 volts max. As the charger power increases, where the charger plugs in will naturally change. Residential outlets can handle chargers up to about 1.2 kilowatts in North America and about 2 kilowatts in Europe. At the 3 kilowatt and the 6 kilowatt level, the charger is going to require a single-phase AC industrial plug or an EV charge station. And as you move up to 10 kilowatts and 20 kilowatts, three-phase AC starts to be needed from an industrial plug or, again, an EV charge station, particularly in Europe. Then finally, getting to today's main topic, charger architecture options. Most people, when thinking about an onboard charger, are probably picturing a single large charger, a big box at a fixed power level, like the charger on the right. But there is another possibility, which is to have a modular charger, which is a system made of several smaller chargers connected in parallel. This has several unique benefits, which we'll get into. But first, what is a modular charging system? What does it look like? How does it work? Here's a typical configuration for a modular charging system using DeltaQ chargers. The orange dashed box in the middle shows chargers that are connected in parallel. On the right, AC power comes from a single source, which could be, again, an EV charge station or a industrial plug. These are single-phase chargers by design, but they can also accept three-phase power if they're arranged in groups of 3 with one charge module hooked up to each phase. On the left, the DC outputs of all the chargers are combined into a single output to charge the battery. CAN bus, shown in the blue lines, lets the chargers communicate with each other and optionally with the battery management system or external vehicle CAN bus. As shown here, the battery pack is controlling the modular charger's output current and voltage over CAN. The key to system operation is a primary-secondary architecture for the chargers. So one charger is designated as the primary, and it controls the operation of the other secondary chargers in order to deliver the needed power, current, and voltage to the battery. Only the primary charger is seen by the outside world, and it shows up as a single high-power charger visible on the externally connected CAN bus system. The secondary chargers are transparent. They aren't seen by the outside world. The primary and secondary chargers have identical hardware and software. So on the production line, you don't need to load special software or mark the chargers differently. They can pick and place any charger in any position, and the modular charging system will just work. The primary charger has a number of functions. It controls the chargers so that they share current evenly. It monitors and controls the total energy efficiency of the system. So for instance, when the system is operating at partial load, the primary charger may choose to turn off some of the secondary chargers so that the remaining chargers can run closer to their peak energy efficiency. The primary charger also monitors the internal temperatures of the secondary chargers to prevent overheating. If a charger does overheat or derate or have a fault, the charge can continue with the remaining chargers. The primary charger controls total AC current draw to avoid tripping a breaker or overheating an AC cord. And finally, the primary charger aggregates, gathers all the diagnostic data, faults, and charge status from the secondary chargers, and it stores it in one place in a centralized data set. Some modular charging systems, like DeltaQs, can offer OEMs an optional interface module to communicate with EV charge stations. This supports both North American and European charge stations, reading the allowable AC current limit and talking over the CAN bus. So we see three key benefits of a modular charging system. First, power is very easily scalable. Up to 6 chargers can be stacked to right-size the output power to the needed level. This gives OEMs a lot of flexibility to offer different charger power options. So for instance, a OEM might offer a lower power base charger, but then also offer the option to add more charger power for customers who have larger battery packs or need a shorter charge time. This is also an opportunity to maybe increase profit with higher margin options. The second benefit is very flexible packaging and mounting. A compact vehicle may not have space for one big rectangular charger, but it might have a package space that's narrow or awkwardly shaped, or even multiple small package spaces where multiple charger modules can fit into the space, where a single large charger couldn't. And finally, a modular charging system can be cost effective. Having a single charger SKU or stocking unit reduces the number of parts that OEMs have to stock and track in their inventory, both for manufacturing and for field support and service. Before we conclude, let's just briefly talk about DeltaQ Technologies. We're a leading manufacturer of battery chargers for both lead acid and lithium-ion batteries. We supply chargers for industrial vehicles and for machine OEMs. Here are some of the industries that we serve and a cross-section of some of our prominent customers. In golf and in utility vehicles, in e-mobility, scooters and motorcycles, in mobile elevated work platforms, scissor lifts and boom lifts, in floor care, vacuums and scrubbers, and in material handling equipment, forklifts and pallet jacks. We're based here in Vancouver, Canada, but we've built up a dedicated global team with local experts on the ground in Europe, in North America, and in Asia, who are ready to help your team to be successful. We can work with you to develop a charger configuration and an integration solution. We can provide training for staff and for service groups. We can help with field issues or field questions about chargers. So let's sum up with some key takeaways. The industry is changing rapidly, moving to battery-powered electric vehicles. That's a great opportunity. It also means that there's an urgent need for onboard chargers that are rugged, reliable, and fully sealed to stand up to and to survive in these harsh onboard environments. OEMs need to offer a wide range of charging power levels to meet the needs of customers who want more runtime and faster charging times. Modular charging systems can help to meet these needs, and they offer several key benefits: easily scalable power, flexible onboard packaging, and a reduced SKU count. Thank you for your attention.